the energy of the nucleus. It is very easy to remove an electron from an atom, but not so for the nucleus. First, I want to define, as we talk about this, I want to define what is an electron volt. We've seen this before, but let me reiterate and describe what an electron volt is. An electron, first of all, electron volt is a unit of energy. Just like joule, just like calorie, it is a unit of energy. I want you to remind you that when we described voltage or potential, that it was an energy per charge. Right? That was our basic understanding for our potential. And an electron volt, which is an EV, is a product of a charge times a potential. So we get it in this way. If I imagine that I have a potential difference where I have positive charges over here, negative charges over here, and let's say that the difference in potential between these 2 points is 1 volt. Then there's a difference in energy. And if I have an electron over here and it travels across this 1 volt, then the energy that it gains is equal to Q times delta V, which is that fundamental unit of charge times whatever the voltage is, in this case 1 volt. So that's where I get the term EV. It's an electron, the fundamental unit of charge, times 1 volt. And EV is the energy that an electron gains when it goes across a potential difference of 1 volt. A hydrogen electron, for example, requires 13.6 electron volts to remove that electron from the atom. So if I draw a very simple hydrogen atom has 1 proton and 1 electron, if it's, neutral. And so in order to remove this electron from the atom, I have to give it radiation that has an energy of 13.6 eV. And then when I do that, that electron will be ejected. It'll have enough energy to escape from the binding force of that proton. Just for reference, a helium proton or neutron, that is the energy to remove a helium proton or an electron, requires a much different energy. It requires 7 million electron volts. So if I imagine a helium atom, which has 2 protons and 2 electrons, if I want to remove one of these protons right here, I have to give it a much bigger source of energy, which has an energy equal to 7 mega electron volts, or 7 million electron volts. So you see, it's a much different thing when I'm talking about the energy required to remove an electron and the energy required to remove a proton. Very, very difficult to mess around with the nucleus of an atom, to change the makeup of the nucleus. If I think about coal and uranium, coal is mostly carbon, and if I have 100 grams of coal, the energy that is wrapped up in that amount of coal is about 10 to the 6 joules, or 10 megajoules. But for 100 grams of uranium, the same amount of uranium has a much larger nucleus. It has 10 to the 13 joules. So notice here that there's a vast difference between the amount of energy that is contained within the molecules or the atoms of these materials, coal and uranium. And this vast energy arises from something we call the strong nuclear force. Remember, potential energy if you recall from the electricity chapter, that potential energy of two charges was really dependent upon the force that was acting upon them, right? We had the Coulombic force, Coulomb's force, the electric force, and the bigger that force was, then the bigger the potential energy was. So if I had two charges here, they have potential energy because if I let them go, they're going to fly apart. And if those charges are bigger, they have more potential energy. So if I let them go, they're going to fly apart even faster. So the force, the bigger the force is, then the bigger the potential energy is. There are four fundamental forces of nature, and we've talked about three of those. The first two are the gravitational and the electric force. Gravitational is the force between two objects of mass. Even though it's very common and we've studied it for many, many years, beginning with Newton and even before Newton, we still don't really understand the gravitational force very well. And then also the electric force, which in a similar way don't really understand it that well. We saw that for both of these that they were inversely proportional to the square of the distance. So if you remember the electric force, it was equal to kQq over r squared. That is, if I were to plot F versus R, it looked like this. And the reason you have this inverse square relationship between F and R, where F is proportional to 1 over R squared, the inverse of the square of R, is because of spherical symmetry. That as you go out, your force is spread out over a 1 over R squared area. Now, the strong nuclear force is the third force. Strong nuclear force, and then also the weak nuclear force. We are most concerned with this. So let's imagine that I have an atom, and an atom consists of protons and neutrons. I'll draw them as zeros, and then there are electrons out around the atom. Those protons are really, really close together. That is, the value for R between those protons within the nucleus is very, very small. So you can imagine that the electric force is very large because R is so small. It is. It's an immensely big force because those protons are so incredibly close together. However, the strong nuclear force is a binding force that binds those nucleons together. So this strong nuclear force, I'm going to call it SNF, just so I don't have to write it out. SNF, the strong nuclear force, is the strongest of these four forces. And even though there is this vast electric force wanting to push these protons apart from one another, the strong nuclear force is the force that binds the nucleons together. And so you might say, well, if the strong nuclear force is so huge, then why does not just everything collapse down into, a little ball of mass in the world? Well, the strong nuclear force only acts over very small distances. About 10 to the minus 15 meters, or about the size, of an atom's nucleus. If a nucleus is bigger, if it's bigger than this, about 10 to the minus 15 meters, then it will be unstable. because that strong nuclear force just doesn't act over those longer distances. And when it's unstable, it will emit nuclear radiation. This radiation is usually very high energy. It is ionizing. That is to say, it is ionizing because it's high energy, that those high energy radiation can come, into the molecules of your body and ionize them, remove electrons from those atoms and molecules, and it can damage living tissue. Many of you will use ionizing radiation as a tool or a diagnostic technique in your career, so it's important to know about it.